Let us continue Pauling scale. Pauling scale is used for determining electronegativity. For this, we will take an example. Now, of H2 plus of F2 gives HF. Here, this H2 bond energy will write it as like this. F2 bond energy will write it like this. HF bond energy will write like this. Now we will find that we will take bond energy of H2. Bond energy of F2 will take here half molecule, therefore 1 by 2. Here half molecule, therefore 1 by 2. We will take average. We will take a average for this. Then we will get a arithmetic mean. We will get. If we want a geometric mean, we have to take a bond energy of H2, bond energy of F2, square root we have to take. This is called a bond energy of HF as per calculated value. Okay, with the help of these two bond energies, we have calculated bond energy of HF. We have calculated. Sorry. Now we will see the nature. This F2 is covalent. This H2 is covalent. So this calculated value gives this covalent nature. Calculated value says that that's covalent nature. It says calculated value says that it's covalent nature. It says. What is actual? What is experiment? What is experiment says? In HF what bond is there means covalent bond is there. HF what bond is there means covalent bond is there. In that there is no doubt. Then electronegativity of H. Electronegativity of H is 2.1. Electronegativity of F is 4. Therefore, F can share the bonding electron cloud to more extent than H. Therefore, in HF, fluorine takes more share of this bond, therefore partial negative. Hydrogen takes less share of this bond, therefore partial positive. Due to this, plus minus attraction is possible. This plus minus attraction leads to polarity. Therefore, here ionic nature is there. This bond contains ionic nature. That means this bond is polar. This ionic nature depends on what? This ionic nature depends on what in the sense? Electronegativity difference. Therefore, electronegativity of F minus electronegativity of H. This difference is directly proportional to percentage of ionic nature. Percentage of ionic nature we can say. This percentage of ionic nature we can call this is as what in the sense? This percentage of ionic nature is depending on what in the sense is directly proportional to what in the sense square root of delta. Square root of delta of which in the sense for HF. This delta is called what in the sense percentage of ionic nature, otherwise polarity of the bond. Now this polarity of the bond, this is called a polarity of the bond. This is nothing but polarity of the bond. The polarity of the bond is equal to what in the sense? Experimental value of HF bond energy minus calculated value of HF bond energy. Now, the calculated value of HF bond energy is calculated using this formula. This formula considers H2 as covalent, F2 as covalent. Therefore, HF has what covalent nature? That covalent nature is corresponding to this bond energy. But what experimental value says in the sense, this experimental value says two things. One is covalent nature, another one is ionic nature. Ionic nature means due to this polarity, partial positive charge and partial negative charge created. Between them, attraction is possible. Therefore, ionic nature is created. So the experimental HF bond energy considers covalent nature as well as ionic nature, but calculated value considers that covalent nature. Therefore, now difference of these two, what gives what in the sense ionic nature bond energy. Ionic nature bond energy is nothing but polarity of the bond, that is nothing but delta HF, we can say. That delta HF, square root of delta HF is directly proportional to electronegativity difference. Electronegativity difference, we can say. Therefore, electronegativity difference, electronegativity of suppose bonded atom A minus electronegativity of bonded atom B is equal to what in the sense, now we can say the proportionality constant, that is 0.208 into square root of delta AB. Delta AB, we can say. Delta is called polarity of the bond, we can say. Now, delta is in what unit means kilocalories per mole. Delta is in unit of kilocalories per mole. Now, we can change the unit into kilojoule per mole. Let us change the unit kilocalories into kilojoule per mole. When you change this kilocalories into kilojoule per mole, this 0.208 becomes how much in the sense 0.1017 into square root of delta AB. Delta AB. Now this delta is called polarity. Polarity of the bond is nothing but experimental bond enthalpy minus calculated bond enthalpy. Calculated bond enthalpy is nothing but square root of bond enthalpy of H2 into bond enthalpy of F2. So from the now we know polarity of the bond. Then out of these two electronegativities, if one electronegativity is known, another electronegativity can be found. So it is called a Pauling scale. Pauling scale. Pauling derived this formula to find a electronegativity. Now in this formula, this delta can be obtained from table. Now out of these two electronegativities, any one electronegativity should be known, for which he considered hydrogen as the arbitrary element. For that, he considered arbitrary value 2.1. So for hydrogen 2.1 value he considered, and from hydrogen rest of the elements electronegativity he found. Sorry. So as per Pauling scale, we know how to find electronegativity. Sorry. Next, Mulliken scale. Now Mulliken scale electronegativity. Now Mulliken scale electronegativity by Mulliken scale and electronegativity by Pauling scale, that we will see. Now electronegativity by Pauling scale, how much is there means it is equal to 2.8 times Pauling scale. Electronegativity of Mulliken scale is equal to electronegativity of Pauling scale into 2.8. Like this is the relation. Therefore, in order to equalize this, Mulliken scale electronegativity is divided by 2.8. 2.8. Therefore, we can say electronegativity of Mulliken scale. Electronegativity of Mulliken scale, in order to equalize into electronegativity by Pauling scale. So what we have to do in the sense that ionization energy plus electron affinity by 2. Average of ionization energy and electron affinity is called electronegativity of Mulliken scale. In order to equalize to Pauling scale, we have to divide this by 2.8. Okay. Now here what is the unit? Unit for this one in the sense electron volt per atom. Electron volt per atom. For this also electron volt per atom. In order to convert this unit into kilojoule per mole. In order to convert this unit into kilojoule per mole. Kilojoule per mole. This is this 2 into 2.8 is given into x. Therefore, now ionization energy plus electron affinity by how much in the sense 544. Now the unit is what means kilojoule per mole. That means electron affinity is in kilojoule per mole. Ionization energy also kilojoule per mole. Okay. So electronegativity by Mulliken scale is equal to electronegativity by Pauling scale. What is the formula in the sense ionization energy plus electron affinity by 544. Here unit of ionization energy and unit of electron affinity is in a kilojoule per mole, we can say. So in this way we have to find a electronegativity, we have to find. So next we have to go for another periodic property called electropositivity. Electropositivity is exactly opposite of electronegativity, that's all. Electron affinity in the sense Gaining of electron. Gaining of electron. Electropositivity. Electropositivity in the sense tendency to donate electron. That's all. Electron gain enthalpy. Electron gain enthalpy means a tendency to gain electron. Electropositivity means a tendency to lose electron, to donate electron. Electropositivity. Set. Then how the metallic nature will be there? Down the group, metallic nature rises. Along the period, metallic nature reduces. Next, non-metallic nature will see. Down the group, non-metallic nature reduces, decreasing. Along the period, non-metallic nature increases, rising. Sorry. Next, we will see nature of oxides. We will see how the nature of oxides will be there. Nature of oxides. Now we will see nature of oxides. Now we will take, for example, sodium. We will take sodium forms its oxide. Sodium oxide we will take. Sodium oxide, if you take that formula is what means Na2. Sodium oxide, if you take that formula is Na2. Aluminium, if you take that formula is aluminium oxide. Aluminium oxide, that formula is Al2O3. Then sulfur, if you take sulfur oxide, that is what means sulfur trioxide, sulfur dioxide, like this possible. For sulfur, what is the formula in the sense? Sulfur trioxide, sulfur dioxide, like this possible. Oxides in the sense we have taken like this example. Sodium oxide on dissolving in water gives what in the sense? Sodium hydroxide. Sodium hydroxide is a base, therefore sodium oxide is basic oxide. Next, SO3, sulfur trioxide on dissolving in water, we will get sulfuric acid. Sulfuric acid is acid, therefore SO3 is called acidic oxide. SO3 is acidic oxide in the sense it is having dominant acidic nature. Na2O is basic oxide in the sense it is having dominant basic nature. Al2O3 is what in the sense? Amphoteric oxide. Amphoteric oxide in the sense it is having both acidic nature as well as basic nature. Like that we can say. So, oxides in the sense three categories we can say. One is basic oxide, one is acidic oxide, one is amphoteric oxide we can say. How down the group, what happens to the nature of oxide? Down the group, basic nature of oxide increases. Down the group, if you see, basic nature of oxide increases. Basic nature of oxide increases down the group. So, along the period, left to right, what happens to the acidic nature? Acidic nature of oxides increases. Acidic nature of oxides increases along the period. Now we will take second period, we will take, otherwise we will take third period. Third period we will take, first element is sodium. Sodium we will convert into sodium oxide. Next magnesium into magnesium oxide. Next aluminum into aluminum oxide. Next silicon into silicon dioxide. Next phosphorus into phosphorus oxide. It is phosphorus pentoxide. Then sulfur into sulfur trioxide. Then chlorine into chlorine heptoxide. Chlorine heptoxide we have seen. So how the nature of oxides will be there for these cases, that we will see. Sodium oxide is a strongly basic. Sodium oxide is a strongly basic, we can say. MgO, magnesium oxide, is a weakly basic. Aluminum oxide, Al2O3, is amphoteric. Aluminum oxide is amphoteric. Silicon dioxide is weakly acidic. Silicon dioxide is weakly acidic. P4O10 is weakly acidic. P4O10 is weakly acidic. SO3 is a strongly acidic. SO3 is strongly acidic. Cl2O7 is strongly acidic. Cl2O7 is strongly acidic. So in the third period, how the nature of oxides is there, see. So along the period, acidic nature of oxides increases. So whatever the oxide you take, that will have acidic nature as well as basic nature. In some cases, one will dominate. So if you take sodium oxide, it is having acidic nature as well as basic nature, but basic nature is dominating, therefore it is called basic oxide. If you take SO3, it is having acidic nature as well as basic nature. Acidic nature is dominating, therefore it is called acidic oxide. But Al2O3 is amphoteric oxide, therefore acidic nature as well as basic nature, both we have to consider for this Al2O3, we have to consider it. So how the nature of oxides? How the nature of oxides vary in a group as well as in a period, that we have seen. Next we will take a first group, we will take, that is alkali metals. We are taking alkali metals. In the alkali metals, lithium element. Next to lithium is sodium, next to potassium, next to rubidium, next to cesium, next to francium. It is alkali metals. In the alkali metals, if you see, in this alkali metals, lithium reacts with the nitrogen to give lithium nitride. This is called what means lithium nitride, you can say. This rest of these elements, francium we can leave because it is radioactive. These are not reacting with the nitrogen, no reaction. Lithium reacts with the nitrogen to give lithium nitride, but the rest of the elements are not reacting with the nitrogen. Next, we will see lithium we will convert into bicarbonate, that is lithium bicarbonate. Similarly, sodium, potassium, rubidium, cesium we will convert into bicarbonate. So they are converted into bicarbonates. These bicarbonates are solid, but lithium bicarbonate is liquid. So you see that lithium differs from rest of the elements in its group. So in each group, first element will vary from rest of the elements. So lithium is showing somewhat difference from rest of the elements of its group. That is, we have seen two examples here. We have seen. Now we will take what in the sense. So we are saying lithium reacts with the nitrogen. Lithium reacts with the nitrogen to give what in the sense lithium nitride. Sodium, potassium, rubidium, cesium do not react. No reaction. Next we will take magnesium. Magnesium will react with the nitrogen to form magnesium nitride. Magnesium nitride, we can say. Magnesium we will convert into bicarbonate. This bicarbonate is in what state, means liquid state, as like lithium. So lithium bicarbonate is in liquid, magnesium bicarbonate also is in liquid. Therefore, lithium shows some similarities with the magnesium. So we will take alkali metals first a group, lithium, afterwards sodium we will take, lithium, sodium, potassium, rubidium, cesium. Then second A group we will take. Second A group is what means beryllium, magnesium, aluminum, magnesium, calcium, strontium, barium. Now if you see, this lithium and magnesium shows some similarities. Likewise, we will take third A group. Third A group will take third A group boron, aluminum, gallium, indium, thallium. Here beryllium and aluminum showing similarities. For which we will take beryllium carbide. Beryllium carbide on hydrolysis gives methane gas. Aluminum carbide on hydrolysis gives methane gas. So beryllium and aluminum shows some similarities. Next we will take fourth A group, that is carbon, silicon, germanium, tin, lead. Here boron and silicon shows some similarities. Boron and silicon shows some similarities. These are how it is there, means just like diagonal. Therefore, these are called a diagonal relationship. Diagonal relationship, we can say. Diagonal relationship. So, due to diagonal relationship, lithium magnesium shows similarities. So, which are diagonal pairs? Diagonal pairs in the sense one is lithium magnesium, next one is beryllium aluminum, Next one is boron silicon. These are diagonal pairs. In rest of the cases, diagonal pairs are there, but that is not dominant when compared to its own group. That means lithium shows more similarities with magnesium than its own group. Like this, these three pairs. In rest of the groups, the first element shows more similarities with its own group than with the diagonal pair. Therefore, diagonal pairs mainly, which are diagonal pairs, means these three are diagonal pairs. So, now, why these three elements, these three diagonal pairs are having similarities? That we will see. Similarities are there. Why is it so? That point we will see. Now we will take lithium and magnesium diagonal pair. Lithium and magnesium diagonal pair we will take. Now we will see atomic radius of these two. So first we will say atomic radius. Lithium atomic radius is 1.52 angstrom. Magnesium atomic radius is 1.6 angstrom. Difference is not much. Ionic radius we will see. Next we will see ionic radius. Li plus. Li plus ionic radius is how much in the sense 0.76 angstrom. Li plus ionic radius is 0.76 angstrom, and Mg2 plus ionic radius is 0.72 angstrom. 0.72 angstrom. Ionic radius also not having much difference. Next we will see electronegativity. We will see electronegativity of lithium. If you see, that is 1. Electronegativity of lithium is 1, and magnesium if you see, that is 1.2. Electronegativity is not having much difference. Then polarizing power we will see. Polarizing power. Polarizing power. Polarizing power is equal to what in the sense ionic charge by ionic radius. It is called polarizing power. Ionic radius. Now, ionic charge for lithium means +1, for magnesium means +2. Magnesium means ionic charge is +2, lithium means +1. That is relative charge. And ionic radius in the sense lithium means 0.76, magnesium means 0.72. This is called polarizing power. This polarizing power is how much for lithium? For lithium, polarizing power is 1.32. For magnesium, polarizing power is 2.78. So the difference is not much in lithium and magnesium regarding atomic radius, ionic radius, or electronegativity. Therefore, lithium shows similarities with magnesium. This pair is called a diagonal pair. This pair we can call it as a diagonal pair. We can call cell. Now, this is about periodic classification of elements. Next, we will go for next chapter, that is chemical bonding. We will go to next chapter. The next chapter is called what in the sense chemical bonding we will take.